Hello everyone and welcome to the quantum image processing playlist. I'll be taking you in the next series of videos on the various modalities or the various schemes of encoding classical images into quantum circuits. We'll also be going over the code implementation. But first we need to walk over the intuition, and this series of videos would be very useful for someone getting into quantum image processing or even data processing in general, from the basics. So with that said, let's get started. So let's say we have an image which is a two-dimensional image. We have 2 by 2. We're going to be very simple here. The important thing is to get the intuition and the principles. You can always apply them anywhere. And we have only 4 pixels: 0, 255, 128, and 64. 2 by 2 image, 1 channel. This just, we can say the red channel, or we can say it's a grayscale image. If it were an RGB, you would have 3 other channels, but we only have 1 here. Now let's say P is our number of pixels and we only have 4 pixels here: 1, 2, 3, 4. So how does this translate into a quantum circuit is the question we seek to answer in this video. To do that, we would first need to calculate the amount of resources that are needed to adequately represent this, and that boils down to the number of qubits in a quantum circuit. So let's ask ourselves, how many qubits are needed? We start by representing our qubit number as Q, and in the introductory quantum computing class, it's known that if you have Q qubits, you can represent a total of 2 to the power Q states. So what we want to do is to represent these unique states with our pixels here. We only have 4 pixels, and how those are distinct values, and so we need 4 distinct quantum states to be able to represent those 4 pixels. And if we do that and calculate the number of qubits needed, we get, so if P is equal to 4, then Q gives us 2 here. So we need 2 qubits to adequately represent 4 states. Generally, you would want this number here to be greater than or equal to P. You don't want it to be less, because in that case you can't represent all of your classical states. It's good you have more, so you have more room for all of this. So now we have our 2 qubits initialized to 0 states, and let's visualize how many states this represent. We have the 0, 0, the 0, 1, 1, 0, and 1, 1. And generally, given a 2 qubit system, we can represent the state as alpha 1 of 0, 0 plus alpha 2 of 0, 1 plus alpha 3 of 1, 0 plus alpha 4 of 1, 1. Awesome. These are what we call the amplitude values. So alpha 1 squared plus alpha 2 squared plus alpha 3 squared plus alpha 4 squared should be equal to 1. And when you square it, you convert the amplitude to a probability. And in probability class, we know that the total probability should be equal to 1, and that's why all of these squares must equal 1, meaning that's the total probability. If you've never encountered this equation before, I would encourage you to visit introductory quantum computing class, and these videos are just to build on that knowledge. Else you can comment, and I'll do a very quick 1 video introductory overview of these stuff. So now we have our 2 qubit system, and these are the states, and these are the amplitudes, and these are the probabilities. What we want to do today is to encode these pixel values as the amplitudes here. And this brings us to the name of this encoding scheme. We call it the amplitude encoding. Now, these pixel values would need to be processed in a way to satisfy this equation here, such that these values would now be the pixel intensities. And the basis vectors of the 2 qubit system would be the indices of each of the pixels. What do we mean by that? We have column 0 here, and sorry, this is a row. We have row 0 here and row 1, and then we have column 0 here and then column 1. Forget about this 2. Now at index 0, 0, we have the pixel intensity 0. At index 0, 0, we have the pixel intensity alpha 1. So we want to transform this pixel state to be equal to alpha 1, alpha 2, alpha 3, and alpha 4. And at index, let's say 1, 0, at index 1, 0, we have 1 to 8, which is alpha 3, So that is the correlation we want. To do that, we need to normalize this particular image. We need to normalize all of these values. And to normalize them, we'll find the norm, and after finding the norm, we divide each of these by the norm, and that should satisfy that equation over there, and you can check it out later on. So we're going to find the norm, and that is the image over the maximum value here. There are actually two ways. You could just go ahead and find the norm of these values and divide each of them by that, but we will be first converting them to 0, between 0 and 1 range, just for rigor. So image over 255, that's the maximum pixel value here, and that should transform this to 0, 1, 128 over 255 and 64 over 255. So 255 over 255 will give us 1, 0 over 255 will give us 0, and that. And after that, we square this. IM over 255 all squared would give us 0, 1, 128 over 255 all squared, 64 over 255 all squared. And then after that, we sum all of these values. So the sum of IM over 255 squared is equal to, I hope you understand this notation, is 0 plus 1 plus 128 over 255 all squared plus 64 over 255 all squared. And to find the norm, we get the square root of this, find the square root of this, and that is the norm. We can say the magnitude. So after finding this, then we divide this state, which is a range between 0 and 1, by the norm. And by doing that, we get, and this particular notation here, this particular one, that's 1 over the norm of 0, 128 over 255, 164 over 255, should match to these values, alpha 1, alpha 2, and alpha 3 and alpha 4. These values should match. So alpha 1 is 1 over the norm times 0, which is 0. Alpha 2 is 1 over norm here, and alpha 3 is 1 over the norm times 1 over 2 times this, and accordingly. So you can verify this. So we have this condition met, and that means we can now adequately represent our 2-qubit quantum state with this. Pick your qubits in the 0 state. You have your amplitudes, which are the pixel intensities. You apply gates to these qubits to tune them in such a way that they would have these amplitudes or these probabilities when they are measured. And by doing that, you've successfully encoded your image. The idea here is to see how the image is encoded, but generally after encoding this, so this is the encoding. After that, you would have some machine learning QML processes on your image. But we are stopping here. We only want to learn how to encode these classical images. And then after that, we will be measuring them. So let's say 1,000 shots. That's what's written in the code. We have 1,000 shots. And for 1,000 shots, we would see the probability, or we would get the count of each of these basis vectors emerging. So let's say the count for the state, of 0, 1, 0, 0 is, let's say, C1, and the count for the state 0, 1 is, let's say, C2. And so these are just counts. They don't speak probabilities. To convert them to probabilities, you have the count over the total number of shots. That's 1,000. And this should give us the probability of this state occurring. After you get those probabilities, remember that the alpha 1 squared is equal to p. And so to get alpha 1, what you do is you find the square root of the probability, and you get your pixel intensity. And after you get alpha 1, then you can do the rest of the process to get back to your pixel intensity. Here we have Qiskit initialized. Let me just run this again. We have this here. Now, this is the same process. We have our image initialized here. Shape is 2 by 2, and the width and the height are obtained, and the pixel number is obtained here. So you can increase this number, and then these would change accordingly. And this is the normalization process. You divide the image by the max, you square all of them, you sum them, you square root it to get the norm square, the magnitude, and you divide the norm image by the magnitude to get your normalized image, and this is the amplitude encoded image, which satisfies the condition of all this, the sum of all of the squares equal 1. So we compute our number of qubits, and we find the total state, which is 2 to the power number of qubits, and after that we reshape 1D. Okay, we reshape it to one-dimensional array. So this was a 2 by 2 image, and we just reshaped it to 1 by 4 or 4 by 1D image, so we can easily work with it in quantum circuits, in initializing our quantum circuit. And so we printed our values here. You can verify them by yourself, and this is how the image looks like. The display function takes 2 values, but I put in the same image data so that it doesn't throw any error. So this is how our initial image looks like. Now we come to the quantum circuit, and this is the paper here. You can ask. So as you can see, we initialized, this is the main point here. We call qsit.initialize, which is a method in Qiskit to initialize your qubits to a specific state. So we have initialized it to a state that encodes our amplitudes, our referenced amplitude. So you put your amplitude encoded image here, which is basically these values that you have, and Qiskit will do the rest. Now I used decompose in order to see what's actually happening, but if you just use the draw, you would find this block image. It just tells you that it's been initialized to this, but it doesn't show you the gates that have been used. So I use the decompose to see those values, and these are actually unitaries, meaning if you pick these 0, 0 qubits, you apply this unitary with these parameters and this, and apply C0. If you do the mathematical rigor, even on paper, you should be getting these qubits initialized to the states that you wanted. So that is what's happening in the background, and there is more to how they found these values for these unitaries. You can look that up. After that, the circuit is simulated. The shots are 1,000, and after that we measure each of them, and 0, 1 is 764 times, meaning 764 but plus 188 plus 48 should give us 1,000 shots. That's the total. And so to get our probabilities, what we do is we divide the number of the counts by the total shots, and this gives us these values. We divided the amplitudes by the sum of the amplitudes, which is the total shots, and then to find the pixel value, you square with the probability as we've done and multiply by 255, and then we got these values. We had to insert 0 in the first index because the pixel intensity value there wasn't detected. So the quantum circuit says its probability of occurring is 0, so they didn't capture it, but then we put it back here since we know what we're doing. And then we reconstruct it. So this is the initial image, and this is the reconstructed image. And as you can see, there are some discrepancies. This is 255 and this is 222. At least it's closer. So let's increase the number of shots. So now we have 760. Those are the counts, and then we find the, has it changed? I think this is still 222. We can find the C, okay, the probabilities are here. Let me just increase it because I didn't think it has changed. Okay, I think I was not running the last cell to generate the image. So let's do this again. Oh my goodness, I know why. So we have been building the circuit on itself, and that's why we're seeing these values. So let's just rerun this to start the entire process. Now we get it here, and then we run this. Awesome. So we have out of 100 shots 77, 23, and these are the new pixel values, and we can see that this has changed. Let us increase the number of shots here to, this is 100k, but then we start this circuit again, we reinitialize it, then we get our new values here, and then awesome, this is also updated, and I can say at least it's a little bit closer. So that's it for this video, how to encode an image using quantum amplitude encoding. I would include the link to this particular method, how they found the unitaries.